Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed. Before we get started, here's a fascinating fact. Most of what makes up the universe, nearly 95% of it, is completely unknown to us. We do not know what it is. Tonight, we will drift slowly through the questions that sit at the very edge of human knowledge. The pull of unseen matter, the stretching of space itself, the birth of everything, the strange missing twin of matter, the heart of a black hole, the far and quiet end of all things, the silence among the stars, the shape of space, and the one law that might tie it all together. Let's dive in. Part 1. Why the universe is speeding up and not slowing down. For most of the last century, astronomers assumed one simple thing. Gravity pulls. Every galaxy pulls on every other galaxy, so the expansion of the universe, set into motion by the Big Bang, should be gradually slowing down, like a ball tossed upward, gently losing speed as gravity works quietly against it. In 1998, two teams of astronomers set out to measure exactly how much that expansion was slowing. They studied a certain kind of exploding star called a Type 1a supernova, prized because each one burns with nearly the same brightness, making it a reliable marker for measuring vast cosmic distances. What they found startled both teams completely. The far-off supernovae were dimmer than expected, meaning they were farther away than they should have been if the universe were merely slowing down. The only explanation that fit the data was almost unbelievable. The expansion of the universe was not slowing. It was speeding up. Something was pushing space apart, and pushing harder as time went on. Scientists gave this unseen force a name, dark energy, though the name explains very little. It behaves unlike anything else we know, growing stronger not because it is gathering, but simply because there is more space for it to fill as the universe stretches. The two teams who uncovered this, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, received the Nobel Prize in Physics in 2011. Their careful, quiet work upended a century of assumption. Gravity was still real, still faithful, still holding galaxies and stars together. But something else, something far stranger, now governed the universe on the largest scale. Dark energy is thought to make up roughly 68% of everything that exists, dwarfing both ordinary matter and dark matter combined. It fills every corner of space evenly, and its effect grows as space itself grows larger, meaning the acceleration it drives will likely continue, gently but relentlessly, for a very long time to come. One leading idea treats dark energy as a property built into space itself, something Einstein once called the cosmological constant, a term he added to his equations and later set aside, unsure if it was needed. Decades after his passing, the data proved him closer to right than anyone expected, though the reason behind the number itself remains unexplained. Other scientists propose something they call quintessence, a field that might change gradually over great stretches of time rather than staying fixed. If dark energy shifts in strength, the far future of the universe could unfold quite differently than if it remains constant. Distinguishing between these ideas requires measurements of extraordinary precision still being gathered today. What strikes me most is how quietly this force operates. It offers no glow, no pull you could ever feel, no signature, but the slow drifting apart of galaxies across billions of years. And yet, it may be the single largest influence shaping the future shape of everything that exists. So somewhere above you tonight, space itself is gently loosening its own fabric, expanding a little faster with every passing moment, carrying galaxies farther from one another in a hush too vast and too slow for any of us to ever notice in a single lifetime. Part 2. What dark matter might truly be made of. In 1933, an astronomer named Fritz Zwicky studied a distant cluster of galaxies called Coma. He measured how fast the galaxies moved and found something strange. They moved far too quickly to be held together by the gravity of the matter he could see. Something invisible had to be holding them in place. Decades later, in the 1970s, an astronomer named Vera Rubin studied the edges of spinning galaxies. By every known law, the stars at the outer edges should have moved slowly, drifting away from the pull of the galaxy's center. Instead, they moved at nearly the same speed as stars near the core, held firmly by something unseen. This unseen presence became known as dark matter. It does not shine. It does not block light. It only reveals itself through gravity, through the gentle bending of starlight as it passes nearby, through the way galaxies cling together instead of drifting apart. We can see its fingerprints everywhere, yet we have never once seen the hand itself. One of the clearest signs came from a formation astronomers call the Bullet Cluster, two great gatherings of galaxies that once passed through one another. The ordinary matter, the gas and dust, slowed and piled up in the middle, but the gravity, traced by the bending of light, kept moving outward, as if something invisible passed straight through, untouched. So, what is it made of? For decades, scientists proposed that dark matter might be made of faint, slow-moving particles called weakly interacting massive particles, often shortened to WIMPs. Deep underground laboratories, shielded from the noise of the surface, have spent years listening for the faintest whisper of one striking ordinary matter. So far, only silence. Other scientists favor a lighter possibility called the axion, a particle so gentle it barely touches anything at all. Detectors tuned like radios, searching across a vast range of frequencies, hope to one day catch its signal. Neither the WIMP nor the axion has ever been directly caught. Both remain candidates, waiting patiently in the dark for confirmation. For a while, some proposed dark matter was simply ordinary matter we had missed. Dim stars, cold planets, drifting bodies too faint to notice, called massive compact halo bodies. Careful surveys searched for their gravity-bending distant starlight. The numbers never added up, nowhere near enough to explain what astronomers were measuring. What makes this question remarkable is its scale. Dark matter is thought to make up about 27% of everything that exists. It shaped the structure of the cosmos, gathering gas into the great webs and clusters where galaxies like our own eventually formed. Without it, galaxies as we know them may never have come together. Tonight, somewhere far above you, invisible matter is quietly threading through the space around our galaxy and through the space around you this very moment. It asks nothing of you. It causes no harm. It simply holds the universe in its gentle, unseen grip, the way a hand might rest lightly on a shoulder in the dark. We do not know, not yet, exactly what it is. Not knowing is not the same as failing. It is simply where the story stands right now, an open door rather than a locked one. And this vast, patient mystery keeps drifting quietly alongside every galaxy, holding the heavens gently together while we rest. Part 3. The disagreement over how fast the universe expands. Nearly a century ago, an astronomer named Edwin Hubble noticed something remarkable. The farther away a galaxy sat, the faster it appeared to be moving away from us. This simple relationship gave rise to a number, now called the Hubble constant, describing exactly how quickly the universe is stretching apart with each passing moment. Measuring that number should, in theory, be straightforward, yet two very different methods, each careful and each trusted, keep returning two different answers, and decades of refinement have only sharpened the disagreement rather than resolved it. The first method looks nearby, using pulsing stars called Cepheid variables, whose brightness rises and falls in a steady rhythm tied directly to their true brightness. By comparing that true brightness to how dim they appear from here, astronomers calculate their distance, and from there, how quickly space is expanding around them. This local method refined for years using the Hubble Space Telescope, consistently returns a value near 73 kilometers per second for every distance unit called a megaparsec, meaning space stretches by that much for every added stretch of that vast distance. The second method looks instead at the oldest light we can observe, the faint glow left over from the early universe, called the cosmic microwave background. A spacecraft named Planck mapped this glow in extraordinary detail, and from its patterns, scientists calculate a Hubble constant closer to 67 kilometers per second per megaparsec. The difference may sound small, only a few units, but in cosmology it is anything but small. It suggests either a quiet flaw hiding somewhere in one of the methods, or something genuinely new about the universe that neither method alone can explain, some unknown ingredient still missing from our models. Astronomers have checked and rechecked both methods for years, refining their tools, gathering larger samples, searching for any hidden error. The gap has not closed. If anything, as the measurements have grown more precise, the disagreement has only become more difficult to dismiss as simple mistake. Some propose that dark energy may not be perfectly constant after all, gently shifting its strength over great stretches of time. Others wonder if an unfamiliar form of radiation filled the early universe, subtly altering the ancient light we now study. No single idea has yet won wide agreement among scientists. This gap has come to be called the Hubble tension, a fittingly gentle name for a puzzle that keeps two of the most careful measurements in astronomy quietly disagreeing with one another, each grounded firmly in trusted physics, each seemingly correct, and yet somehow both cannot be. Whatever the answer turns out to be, it likely holds something we have not yet come to see, some quiet detail of the cosmos still hidden just beyond our current reach, waiting patiently for a sharper instrument or a clearer thought to finally bring it into view. Part 4. What came before the beginning we can observe? Nearly 14 billion years ago, by the best measurements we have, the universe as we understand it began. Space itself was smaller than anything we can picture, unimaginably hot, unimaginably dense, and from that state it began to stretch outward, cooling gradually as it expanded into the vast structure we now call home. This moment is often called the Big Bang, though the name can mislead. It was not an explosion happening somewhere within space. It was the beginning of space itself, and of time alongside it, unfolding everywhere at once, rather than rushing outward from any single point we could locate. Our equations, remarkably, can describe the universe back to a fraction of a second after this beginning, a period so brief it is nearly impossible to picture in ordinary terms. But push further back, closer to the very first instant, and the equations themselves begin to break down completely. That earliest sliver of time is called the Planck epoch, a period so small and so extreme that general relativity, our finest theory of gravity, no longer gives sensible answers. To understand what truly happened there, physicists believe we would need a theory that unites gravity with quantum mechanics, one we do not yet possess. Because of this, the honest answer to what came before the beginning is that we do not know, and we may not currently possess the tools to know. It sits just past the edge of our measurements, in a region where our finest theories quietly fall silent, rather than confidently continue speaking. One widely supported idea, called inflation, proposed by physicist Alan Guth in 1981, suggests that space expanded with astonishing speed in the earliest sliver of a second, smoothing the universe into the remarkably even shape we observe today. Inflation explains much of what we see, though what triggered it remains uncertain. Some physicists propose that our universe may be one among countless others, each with its own beginning, drifting apart in some larger structure we have no way of observing directly. Others propose the universe may have bounced from an earlier state of contraction rather than beginning from true nothingness at all. None of these ideas can currently be tested in the way science usually demands, through direct observation or repeatable measurement. They remain thoughtful, mathematically grounded possibilities, offered honestly as possibilities, not as settled fact, by scientists who are careful to say so themselves. There is something calming, oddly enough, in admitting we do not know. It means the universe still holds a secret at its very core, a quiet, unopened question resting gently at the start of everything, patiently waiting for a future mind, perhaps generations from now, to finally understand. For tonight, it is enough simply to sit with the mystery, to imagine that first sliver of time without needing to solve it, and to feel quietly how strange and wonderful it is that we exist at all, so long after that first hushed unfolding of space and time. Part 5. Why matter outnumbers its vanished antimatter twin. Every particle of ordinary matter has a mirror twin, one with the very same mass but the opposite electrical charge, known as antimatter. When a particle meets its antimatter twin, both vanish completely, their mass turning fully into a burst of pure energy, leaving nothing of either one behind. According to our best equations, The earliest universe should have created matter and antimatter in perfectly equal amounts. If that were truly the case, the two should have met and vanished together almost entirely, leaving behind a universe filled only with light, with no stars, no planets, and no astronomers to ever ask the question. And yet, here we are. Stars shine, galaxies turn, and matter clearly won out. For every roughly 1 billion pairs of matter and antimatter that likely existed early on, it seems one extra particle of matter survived. That tiny surplus is the entire reason anything solid exists in the universe at all. Physicists call this the baryon asymmetry problem, and it remains one of the most puzzling unanswered questions in all of physics. Why would nature favor matter so slightly, yet so decisively, when every known law suggests the two should have been created in perfectly equal measure from the very start? In 1964, physicists James Cronin and Val Fitch discovered something called charge parity violation while studying the decay of particles called kaons. It showed that nature does not always treat matter and antimatter with perfect symmetry, a small but real crack in an otherwise balanced rulebook. This discovery mattered greatly because in 1967, physicist Andrei Sakharov proposed that such a violation was one necessary ingredient for matter to end up outnumbering antimatter. Yet the amount of asymmetry found in kaon decay, and later in particles called B mesons, is far too small to account for the imbalance we observe. Modern experiments, including work at the Large Hadron Collider using a detector called LHCb, continue searching for additional sources of this asymmetry, studying rare particle decays with extraordinary precision, hoping to uncover some overlooked process from the earliest moments of the universe that might finally close the gap. Some physicists wonder if neutrinos, among the strangest and lightest particles known, might hold part of the answer, behaving slightly differently than their antimatter counterparts in ways not yet fully measured. Great underground laboratories are studying neutrinos closely, hoping their quiet behavior might reveal what visible matter alone cannot. For now, the imbalance remains unexplained in full. We know it happened. We can measure its result all around us, in every star, every planet, every gentle breath you take tonight. But the precise mechanism, the exact reason matter tipped the scale, is still being carefully searched for. It is a strange thought to sit with, that your own body, every atom within it, exists only because of a very small, very ancient imbalance, a tiny asymmetry favoring existence over emptiness, tipping the earliest universe gently toward matter, toward light, toward everything that would eventually become you. Part 6. What waits inside a black hole's hidden core? A black hole forms when a great deal of mass gathers into an extremely small space, creating gravity so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Beyond that boundary, our understanding of the interior becomes far less certain and far more strange. General relativity, Einstein's theory of gravity, predicts that at the very center of a black hole lies a point called a singularity, where density becomes infinite and the equations themselves stop giving meaningful answers. Most physicists suspect this infinity is not truly real, but rather a sign that the theory has reached its limit. To understand what actually happens at the center, physicists believe we need a theory that successfully unites gravity with quantum mechanics, the physics that governs the smallest particles. Such a theory does not yet exist in a form scientists broadly agree upon, leaving the true heart of a black hole essentially unknown. In 1974, physicist Stephen Hawking proposed something remarkable: that black holes are not perfectly black after all. Due to quantum effects near the event horizon, they slowly release a faint form of radiation, now called Hawking radiation. And over unimaginably long stretches of time, they gradually shrink and fade away. This discovery raised a troubling puzzle, now known as the black hole information problem. When something falls into a black hole, does the detailed information describing it vanish forever once the black hole eventually evaporates? Or is it somehow preserved and released again, hidden quietly within that faint outgoing radiation? If information truly vanished forever, it would break a deep principle in quantum physics, one holding that information should never simply disappear from the universe. Most physicists now lean toward the idea that information is somehow preserved, though exactly how remains genuinely unresolved and actively debated among leading researchers. One idea, called the holographic principle, suggests that everything falling into a black hole may be described entirely by information encoded on its outer surface, the event horizon itself, rather than within its interior. It is a strange and beautiful idea, treating the inside almost as a kind of shadow cast by the surface. In 2012, a group of physicists proposed something called the firewall idea, suggesting that anything crossing the event horizon might encounter a wall of extreme energy rather than passing through gently as relativity predicts. This clashed directly with long-standing expectations, and the debate around it remains unsettled. We have, remarkably, captured images of the shadow a black hole casts against its surrounding glow, thanks to a global network of radio telescopes working together. We have detected the faint ripples in space created when two black black holes merge, yet the true nature of their interior remains entirely beyond direct observation. So the center of a black hole remains one of the most profound unanswered questions in physics, a place where our finest theory of gravity quietly admits defeat, and where the truth may only be found once gravity and the quantum world are finally, gently brought together as one. Part 7. Will the universe end in ice or in fire? Once astronomers confirmed that the universe is not only expanding, but expanding ever faster, a new question naturally followed. What happens, given enough time, to everything that exists? The answer depends entirely on the true nature of dark energy, a force we still do not fully understand. The scenario currently favored by the data is sometimes called the Big Freeze, or heat death. In this future, expansion continues indefinitely. Galaxies drift farther and farther apart. Stars gradually burn through their fuel, and the universe grows colder, darker, and quieter across trillions of years, far beyond the current age of everything. In this slow ending, no dramatic single moment marks the finish. Instead, the last stars fade one by one. Black holes slowly evaporate through Hawking radiation over spans of time almost impossible to picture, and eventually only a thin, cold, nearly empty stretch of space remains, drifting in silence. A second possibility, called the Big Crunch, imagines the opposite outcome, where expansion eventually reverses and the universe collapses back upon itself, mirroring its own beginning in reverse. Current measurements of accelerating expansion make this outcome seem unlikely, though earlier generations of astronomers once considered it the most probable ending. A third and far more sudden possibility is called the Big Rip. If dark energy grows stronger over time rather than remaining steady, its outward push could eventually overcome every other force, gradually pulling apart galaxies, then stars, then planets, and finally even atoms themselves in the universe's final moments. Current observations lean firmly toward the gentler ending, the Big Freeze, since dark energy appears remarkably steady rather than strengthening. But the honest truth is that our measurements, however careful, cannot yet rule out the other possibilities completely, and refining them remains an active and ongoing pursuit. Whichever path unfolds, the timescales involved are almost impossible to hold in the mind. We are speaking of trillions upon trillions of years, a span so far beyond a single human life, or even the life of our sun, that it becomes less a countdown and more a kind of quiet, distant horizon. There is something gently steadying in this vastness, Whatever ending eventually comes, it lies so unimaginably far ahead that it holds no bearing on tonight, or tomorrow, or any life that you'll ever be lived by anyone reading these words. It is simply the shape of forever, sketched faintly in the data. Some physicists find comfort in the sheer scale of time remaining, noting that even the Big Freeze allows almost unfathomable stretches for anything that might come after us, while others find quiet meaning simply in knowing the question is being asked carefully, honestly, without any need to rush toward an answer. For now, the universe simply continues, expanding a little faster with every passing year, carrying us gently along, its distant ending still unwritten in full, still being measured, still being reconsidered, one careful observation at a time, far above the small and steady rhythm of your breathing tonight. Part 8. The quiet question of whether we are alone. In 1950, physicist Enrico Fermi sat at lunch with colleagues discussing the odds of intelligent life elsewhere in the galaxy. Given how many stars exist and how old the galaxy is, he asked a simple, quiet question that has echoed through physics ever since. Where is everybody? In 1961, astronomer Frank Drake proposed an equation to help organize the question, multiplying together factors like the rate of star formation, the fraction of stars with planets, and the chances that life, once formed, might develop into a civilization capable of communicating across the vast distance of space. Many of those factors remain genuinely unknown, which means the equation offers less a firm answer than a way of thinking clearly about an enormous unknown, breaking one impossibly large question into smaller, slightly more approachable pieces, each still resting on assumptions we cannot yet fully test. What we do know has grown considerably since Drake's time. Astronomers have now confirmed thousands of planets circling stars beyond our own sun, many within the temperate range where liquid water could plausibly exist. Worlds capable of supporting life, at least in principle, appear to be far more common than once assumed. And yet, despite decades of careful listening, no confirmed signal from another civilization has ever been received. Since 1960, when astronomer Frank Drake pointed a radio telescope toward two nearby stars in a search called Project Ozma, scientists have continued scanning the sky, and the sky has continued to answer only in silence. This gap between how likely life seems and how quiet the universe actually appears is sometimes called the Fermi paradox, though it may not be a paradox at all, simply a reflection of how difficult communication across such staggering distances truly is, or how rare advanced civilizations genuinely turn out to be. Some propose that intelligent civilizations are common but simply do not last long enough in cosmic terms for their signals to overlap with our own brief window of listening. Others propose that life itself, even simple life, may be rarer than we hope, needing conditions more delicate and specific than we currently understand. Modern searches continue quietly in the background of astronomy, scanning radio and light signals from distant stars, studying the atmospheres of far-off worlds for gases that might hint at biological activity. No confirmed sign has yet appeared, though the tools available today are more sensitive than ever before. There is something gentle rather than lonely in this ongoing silence. It means the question remains genuinely open, that no one yet knows for certain whether a warm world somewhere out there is quietly looking back up at its own night sky, wondering, just as we are, whether anyone else is listening. Perhaps someday an answer will come, or perhaps the silence itself is the answer, at least for now. A reminder that we exist within a universe still largely unexplored, still holding its secrets closely, still leaving room for now, for wonder rather than certainty. Part 9. Is the universe endless, or does it fold back? When we ask about the shape of the universe, we are really asking two related but different questions. Is space curved or flat on the largest scales? And does space stretch on forever, or does it eventually loop back upon itself, like the surface of a very large, very gentle sphere? According to general relativity, space itself can be curved by the mass and energy within it, much like a heavy object resting on a stretched sheet gently shapes the surface around it. On the scale of the entire universe, this curvature could, in principle, be positive, negative, or remarkably close to flat. Astronomers have measured this curvature using the faint, ancient light left over from the early universe, the cosmic microwave background mapped in extraordinary detail by the Planck spacecraft. The patterns in that light suggest the universe is remarkably close to flat, with any curvature, if it exists at all, exceedingly small. A flat universe does not necessarily mean an infinite one, though the two ideas are often confused. Flatness describes geometry, how space bends locally, while infinity describes extent, how far space actually stretches. A universe can be perfectly flat and still, in principle, be finite if it curves back upon itself in shape. One way this could happen is called a torus, a shape resembling the surface of a donut, where traveling far enough in a straight line would eventually return you to your starting point, not because space bent upward or downward, but because it wrapped gently around upon itself in a higher, unseen dimension. If the universe were shaped this way, and small enough for it to matter, astronomers might expect to see repeating patterns in the ancient light of the cosmic microwave background, faint echoes of the same regions of sky appearing more than once. So far, no convincing repeating pattern has ever been confirmed. This leaves two honest possibilities still standing. The universe may simply be infinite, stretching without any edge or end in every direction. Or it may be finite, but far larger than the portion we can observe, its true boundaries hidden well beyond the reach of our current telescopes and instruments. We can only ever observe a limited portion of the universe, a boundary called the observable universe, set by how far light has had time to travel since the very beginning. Beyond that boundary, space likely continues, but we have no way, even in principle, of directly seeing what lies there. So, when we ask whether the universe goes on forever, we are really asking a question our instruments cannot yet fully answer. One that may require detecting some faint pattern, some subtle repetition that has simply not yet been found within the vast, quiet light still arriving from the early universe. It is a strange and calming thought that the true shape of everything, whether endless or gently curved back upon itself, remains genuinely unknown, and that somewhere in that uncertainty is a kind of open invitation to keep looking upward, patiently, without needing the answer tonight. Part 10. The search for one law to explain it all. Physics today rests on two extraordinarily successful theories that remarkably do not agree with one another. General relativity describes gravity beautifully on the scale of planets, stars, and galaxies. Quantum mechanics describes the behavior of particles beautifully on the smallest scales imaginable. Each works perfectly within its own domain, yet the two refuse to merge. This disagreement rarely matters in daily life, since gravity is usually gentle and quantum effects usually small, so each theory works comfortably on its own. But deep inside a black hole, or in the earliest sliver of the universe's beginning, both gravity and quantum effects grow powerful at once, and the theories quietly contradict each other. Physicists have spent nearly a century searching for a single framework that could unite both ideas, often called a theory of everything, though the name promises more certainty than the search has yet delivered. Such a theory would need to explain gravity using the same quantum language that already successfully describes every other known force in nature. One leading candidate is string theory, which proposes that the smallest building blocks of nature are not points, but tiny vibrating strands of energy, far smaller than any particle ever detected. Different vibrations in this framework correspond to different particles, including gravity's own carrier, gracefully woven into the same mathematical fabric as everything else. String theory is mathematically elegant and has produced genuinely beautiful insights, yet it also requires extra dimensions of space beyond the three we experience, dimensions curled up impossibly small, and it has not yet produced a prediction that current instruments are able to directly test or confirm. A second candidate, called loop quantum gravity, takes a different approach entirely, proposing that space itself is not smooth, but made of tiny, discrete loops, woven together at a scale almost impossibly small. In this framework, space is granular rather than continuous, much like how matter itself is made of individual atoms. Both theories remain mathematically serious, developed carefully by leading physicists over many decades, yet neither has been confirmed by observation, and no experiment currently available can reach the extraordinarily small scales where their differing predictions might finally be tested and meaningfully compared against one another. Some physicists suspect an entirely different framework, not yet imagined, may ultimately be needed, one that current thinking has not yet stumbled upon. Scientific history offers gentle precedent for this humility, since both relativity and quantum mechanics themselves once seemed nearly unimaginable before they were finally, carefully worked out. What remains remarkable is that gravity, the very force holding galaxies, stars, and planets gently in place, is also the one force that has resisted joining the quantum picture that so successfully explains everything else. It is, in a very real sense, the single largest unanswered question standing at the center of modern physics. And so the search continues, quietly, in universities and laboratories around the world, carried forward by careful minds working patiently on a puzzle whose final answer may still be generations away. A reminder that even our finest theories are simply the best understanding we have gathered so far, not the final word. And on that note, we come to the end of tonight's journey through the universe's greatest unanswered questions. We wandered through unseen matter, stretching space, disagreeing measurements, and beginnings we cannot fully trace. We sat quietly with black holes, endings, silence, shape, and the search for one guiding law. None of these questions were answered tonight, and that was always the gentle point. Some mysteries are not meant to be solved before sleep. They are meant to be held loosely, admired from a careful distance, allowed to remain exactly as vast and unresolved as they truly are. There is something quietly comforting in not knowing. It means the universe still holds surprises, still keeps a few secrets tucked away, still leaves room for future minds, perhaps even minds not yet born, to look up one night and wonder the very same things you have wondered tonight. Consider for a moment how small your worries feel against a backdrop like this. The bill left unpaid, the message left unanswered, the small ache carried through the day. All of it matters, and yet rests gently within a universe so vast, light takes billions of years to cross it. This is not meant to make your life feel smaller or less important. Quite the opposite. It offers a kind of quiet relief. The sense that you do not have to carry the full weight of everything alone tonight. Patient and unhurried as the universe itself. The same unseen matter holding galaxies together tonight is gently present in the space around you as you rest. The same ancient light that traveled billions of years to reach us is, in its own way, still arriving, still being read, still being wondered about by patient minds. You are made of matter that survived an ancient imbalance. Atoms once formed inside dying stars, carried gently across unimaginable stretches of time to become you tonight, breathing slowly, resting beneath a sky that has been unfolding its mysteries since long before you arrived. Thank you so much for joining me here tonight, for lending me your attention across all these vast and quiet questions, for choosing to spend this time wondering together rather than rushing past the mysteries above us. Until next time,